Okay, so this week we're talking about Chapter 9. Chapter 9 is dealing with hypothesis testing, inferences, but we're not talking about a single population mean or a single population proportion anymore. We're looking at two populations and comparing their means or their proportions. And we're looking at the difference between those. And there's a couple of different ways to do that. So this first section, section 9.1 here, we're going to be talking about independent samples. So let's go ahead and we'll be starting out here, of course, defining what independent samples are. So first step is to distinguish between what is independent samples, and then paired samples is the other option for samples that are not independent. Then we're going to look at performing the hypothesis test using both critical value and p-value, and then looking at constructing confidence intervals for that difference as well. So distinguish between independent and paired samples. Independent versus paired. So a drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to the old drug. Here's one way in which the study can be designed. Two samples are chosen. One sample is given the old drug, and the other sample is given the new drug. After several months, blood pressures of the members of both samples are measured. We compare the blood pressure in the first sample to the blood pressure in the second sample to determine which drug is more effective. This is an independent sample because there's different people in each sample. They're randomly selected, so we're not choosing people to be in one sample or the other. You're not trying to influence them. Now, the problem with this independent design is random chance does wreak a little more havoc with it, because there is a chance that you randomly selected people in one sample that would be more reactive to any medication and accidentally randomly selected people in the other sample that would not have reacted to the medication or whatever the treatment is. So there's a little bit less reliability here. Now the second design here is going to be a dependent sample or paired sample. Drug company, same situation, drug company has this new drug that they want to test. So our design 2, a single group of individuals is chosen. They are given the old drug for a month, and their blood pressure is measured. They then switch to the new drug for a month, after which each blood pressure is measured again. This produces two sample measurements from the same sample, one from the old drug and one from the new drug. So we compare the blood pressures between each. So this is what we call a paired test. It is not independent. We use the same sample and we use two different treatments. Now, I'm not big on the way this sample was set because we used the old drug first and then we did the new drug. I would have done half and half. Half of the still been a paired sample, but have half of the sample use the old drug first for a month, the other half use the new drug first for a month, and then switch. That way you can see maybe the cumulative effect between the two drugs is what caused the blood pressure to be different in that second month. So I mean, that's not a perfect design, but it is a paired design. Paired design is often done as a before and after. For example, like work productivity. A lot of employers feel that productivity falls off after their lunch break. So they'll measure, the production units per hour before lunch and units per hour after lunch for the same person, and they'll subtract. That's a paired test. If they select, several employees and take those measurements. So now we're going to be looking at those independent samples where we have two separate samples randomly chosen, and we're comparing the means and the results of those samples. So we're going to look at the p-value method. In the p-value method, we're going to be using the calculator. We could do it without, but it's easy to use the calculator. So scores on the National Assessment of Educational Progress, mathematics test, range from 0 to 500. In a recent year, the sample mean score for the students using a computer was 309. The sample standard deviation was 29. For students not using a computer, the sample mean was 303 and the standard deviation was 32. Assume there are 60 students on the computer and 40 students that did not use a computer. We can see that the sample mean scores differ by 6 points. 309 was the mean with the computer, 303 was the mean without, the difference is 6. Now we are interested in the difference between the population means, which will not be exactly the same as the difference between the sample means. Remember, this is a point estimate. there's a good chance it is close to the true population mean. In this case, it's close to the true difference of the two population means, but very, very little chance that it's exactly correct. Chances are those two population means are a little bit different themselves, and that difference will be a little bit different. So that's why we do that interval estimate. So it's possible that the difference between the two means is really 0, and that random selection of the samples is what caused the difference of 6 to be calculated. So we have to look at how strong is the evidence that the population mean scores are really different. So we've got mu1 and mu2. Those are the two population means. That was the 309 and the 303. Oh, sorry. Those are the population means, and we don't know what those are. That's what we're trying to make an inference about. The sample means are the 309 and the 303. We have the standard deviations. Those were the 29 and 32. And the sample sizes were 60 and 40. So our null hypothesis is going to be that the two means are equal. That the mean of population 1 is equal to the mean of population 2. The alternatives, again, we have three choices: less than, greater than, or not equal to. In this case, we're saying that the two populations should be equal is what we're trying to test. So I would be thinking that alternative is going to be not equal, but come here. They haven't named that possibility yet. Looking at these now, we have to deal with degrees of freedom. And this is a little bit of a change in this textbook. Some textbooks have a pretty extensive formula that they use to find the degrees of freedom where you combine the sample sizes. This textbook does not do that. What this textbook does is you just take each sample size minus 1. Whichever one's smaller is your degrees of freedom. So this is 60 minus 1 is 59. This is 40 minus 1 is 39. So they'd be using the 39 for their degrees of freedom here. Combining the standard error of the difference of means, it is the standard deviation squared for sample 1 squared divided by its sample size. Standard deviation of sample 2 squared divided by its sample size. Add them together and square root. It's like a weighted average. It's a root mean square for those two. So looking at this, then our test statistic is the difference in their sample means minus the hypothesized difference in the population means. Well, our hypothesis is that the difference is 0, so that's usually 0 is going to go in there. The sample means was, what, 6, I believe? Yes, mean difference is 6. So that'll be 6 there. And of course, these numbers down here, 29 squared, 32 squared, 60, and 40. They'll show us this in the next step, hopefully. Nope. So let's go ahead and we'll fill that in. So this was 6 was our difference in our sample means, minus 0 is our hypothesized difference in the population means. This is going to be the square root of standard deviation. The first standard deviation was 29. So that's 29 squared. That sample size was 60. Second standard deviation was 32, so that's 32 squared. And that sample size was 40. So we've got the 6 minus 0 is just 6. So make sure hit equals first. I'm going to divide by the square root of. I don't have to do any parentheses inside here. It's 29 squared divided by 60 plus 32 squared divided by 40. And I get 0.9533. Appears to be our test statistic. So we have to make sure we've met our assumptions. Both samples are random and each is from a different population. The samples are totally independent from each other, so there's no chance that there's no overlap in the populations, I guess, is part of it. There's no way that somebody could be in each sample or in each population. And it's not a paired sample. We have two populations. each sample size is bigger than 30, or the population is approximately normal. Well, we met both qualifications on this one. So then our normal curve, well, depends on which alternative hypothesis we're going to have. If the alternative is less than, then we're going to reject on the lower tail. If our alternative hypothesis is greater than, we'd reject on the upper tail. Not equal to, we reject on each tail. Remember, it's that significance level split in two. Half goes to each end for the two-tailed test. And this is our same steps for going through hypothesis test as we saw back in Chapter 8. The only difference is, of course, the test statistic is found looks a little bit different here. The National Assessment of Educational Progress tested a sample of students using computer. Okay. So same situation here, but now they're saying let's perform this test at 0.05 significance, so alpha of 0.05. So we checked our assumptions. We have two independent samples from different populations. Both samples are larger than 30, so we don't have to worry about whether they're normal or not. We've got our hypotheses. As we said, the null is always that they're equal, and as I predicted, the alternative is they're not equal. Significance level of 0.05. So we've got our mean for each sample, standard deviation for each sample, and the sample size. And they plug those in just as we did for our test statistic. Now we get 0.953. Well, they actually put the 309 minus 303 in here. We just put in 6 because we already found that difference. But the 0.953 is the test statistic. So our p-value, since this is not equal, we have to find the probability of being greater than 0.953. But we also have to see find the probability of being further away on the other side of the curve. So less than negative 0.953. If we were going to do this on the calculator, our calculator actually has a function built in for two sample tests. So we're going to go to stat, tests, two sample z-test or two sample t-test. Well, here, very seldom will we have the standard deviation for both populations. If we did, we could use a two sample z-test. But here we have the standard deviation of the samples is all we have. So it's a two sample t-test. We have the stats. X bar for the first one is 309. The second one is 303. Oops, sorry, the standard deviation for the first one is 29. Sample size is 60. For the second sample, the mean is 303. 32 is the standard deviation. And 40 is the sample size. Our alternative is not equal to, so we change it to not equal to. Pooled. So we're looking at the pooled here. What pooled is standing for, of course, this is just going through the menus. What pooled is asking is, are we pooling the standard deviation? If we don't pool the, under certain circumstances, we can just pool the standard deviation and we don't have to worry about degrees of freedom. If we select no here, it's a little bit tougher calculation, but the calculator can handle it, but it's a little bit more accurate as well. If we select yes, then we're saying that certain conditions exist where we can estimate certain things. And in this case, we don't want to estimate. So we're going to keep that as a no. Basically, general rule, pooled will always be no if we're using the calculator. So let's calculate. And we get that result, 0.953, like we had for our test statistic. P-value is 0.343. So since the p-value of 0.343, right here, is greater than 0.05, greater than alpha, we do not reject HO. So there's not enough evidence from these two samples to conclude that that those means are not equal. So there's not enough evidence to say that there is a difference between those means. If we're doing the critical value method, we would have done the same exact test, only we would have just compared on, we'd have found critical values on the curve. And the same thing goes here. So depending on whether we have a left tail, right tail, or a two-tail test, Our critical values will be located on that bell curve. So this time we're looking at wastewater treatment. We have treatment 1, we have the levels of benzene in those samples, and then treatment 2, the levels of benzene. We want to know how strong is the evidence that the mean concentration is less for treatment 2. So we're trying to see that treatment 2 is less. So HO, H0 is that those two means are going to be equal. The alternative is going to be that the mean for 2 is less, or I might word it as the mean for 1 is greater than the mean for 2. So we've got them plotted there. Here are our hypotheses, just as we predicted. The null is that they're equal. The alternative is that 1 is bigger than 2, or 2 is smaller than 1, however you want to word it. Now we plotted these here to check there is not any major skewness. The top one looks to be a little bit skewed to the right, but not major. So since they're not horribly skewed, then we can go ahead and test. Remember, if they're really horribly skewed, then we've got some issues. They're not normally distributed. We had to do that because these sample sizes were smaller than 30. This sample size here, N1 is only 5, and N2 is only 7. So since those sample sizes were smaller than 30, we had to check to see if they were approximately normal. And we do that with using the skewness on the dot plot there. So we find the critical value from the table. Well, this is alpha of 0.05, which means, since our alternative is greater than, we're looking here. So this probability is 0.05. So this is the cutoff at 0.95. So we can use the calculator and just do 4 degrees of freedom is the smaller of the two. The smaller sample was 5. 5 minus 1 is going to give us 4 degrees of freedom. So on the calculator, we can do an inverse T of 0.95 and 4 degrees of freedom. Now we get the 2.132 just like they had here off the table in the book. On the table in the book, by the way, you would have found that 0.05 on the right tail or 95 on the left tail, whichever way you want to look at it, and 4 degrees of freedom. You'd have followed it across until you forgot to that column that was the 0.05. Okay, so here, compute the test statistic. We've got our values in here. We found the values from each sample. Found the mean, sample mean for each, sample standard deviation for each, and we have the sample sizes. So we plugged in here's the difference between the sample means. We found that. Hypothesized difference is 0. This is the standard deviation of sample 1 squared divided by its sample size, which is 5. The standard deviation of sample 2 squared divided by its sample size, which is 7. We get a test statistic of 1.59. Now, since that's less than our critical value of 2.132, we will not reject. Now, here's an example where we can do on the calculator, we can actually do the list function. So I'm going to go back up to the lists here. We don't get too many examples of this, so I'm going to go ahead and do it. So we're going to go to stat, calc, and I'm going to do the 2 sample t-test, which is 4. And actually what I've got to do before I do that, I've got to go back to edit. Select edit. I'm going to go to my lists. Now my lists are empty here, so I can go ahead and type in the 7.8, 7.6, 5.6, 6.8, and 6.4. Go over to list 2, 4.1, 6.5, 3.7, 7.7, 7.3, 4.7, 5.9. Got them all entered in there, so I'm going to exit out. We're going to stat, tests, 2 sample, t-test. And we're going to go back here and select data. So list 1 is in L1. That's the data for sample 1. Data for sample 2 is in L2. Both of them have frequency. Always leave the frequency of 1. The alternative here is greater than. Keep it as no for pooled. And let's calculate it out, see what we get. So we're going to test statistic of 1.59, exactly what they had here. So we do not reject. Confidence intervals for two population means. Well, we're a similar type of thing. Our margin of error is going to be our Z critical, or and it's actually in this case T critical, I should say. So we're looking at in T, so T critical times that standard error. And that standard error is the square root of S1 squared over N1 plus S2 squared over N2. So let's take a peek. Imagine that we'll compare the effectiveness of a new drug designed to reduce blood pressure. So we're back to the blood pressure example. Now we're imagining that these samples come from two populations again. So we took the two samples of people. One is going to be the sample from the population of people taking the new drug. The other is a sample from population taking the old drug. We're interested in estimating the difference between the population means. So what we're estimating here is mu1 minus mu2. We're using that sample mean of x bar 1 minus x bar 2. That's our point estimate. But we're going to create an interval around that now. So again, here is our standard error formula. As I showed you, the standard deviation of sample 1 squared divided by its sample size plus the standard deviation of sample 2 squared divided by its sample size, and then we square root it. So let 1 minus alpha is our confidence level. So alpha of 0.05 will give us a 95% confidence interval. What that's telling us. So the degrees of freedom, there are two ways to convert it. The simple method is just take the smaller of the two. Software packages will do a complex one. But we've got, again, we had sample sizes of well, let's look at their sample sizes here. So I don't remember exactly what we used. So our confidence interval is going to be exactly what we saw before. It's going to be our point estimate, the difference of the sample means, minus that margin of error. That's the T critical times our standard error. To then a difference in our sample means plus that margin of error, which is our T critical times our standard error again. We have to double check everything again. The samples come from two populations, and they do. They're independent. Nobody can possibly knows nobody that qualifies for both samples, and that's true. And each sample is larger than 30, or the population is approximately normal. So the drug company here has looked at testing this new drug, sample of 15 patients, so that's smaller than 30, so we do have to check to see if it's normal. Their systolic blood pressure is an average of 28.3 millimeters. Standard deviation of 12 millimeters. In addition, another sample of 20 is taken. This group is reduced by an average of 17.1 with a standard deviation of 9.0. So we're looking at the reduction in blood pressure. Assume that blood pressure reductions are approximately normally distributed. So that was big there. We had to assume that they're approximately normally distributed. Then we don't have to worry about the sample sizes being small. So find a 95% confidence interval. So let's check our assumptions. We computed our point estimate. Oops. Sorry. Check our assumptions. We have two independent samples. Yes, the populations are approximately normal. We were told that, so everything is satisfied. Our sample sizes are small, so we had to know that they were normal. So our point estimate, well, the first sample had a reduction in blood pressure by 28.3. Second sample is 17.1, so that's a difference of 11.2. Finding our critical values. We had two sample sizes, 15 and 20, so we're going to use 14 as our degree of freedom. Because 15 minus 1 is 14, 20 minus 1 is 19, so the smaller would be 14. So we looked that up in the table. 14 degrees of freedom, 95% confidence. Remember, confidence interval, that 95% is going to be split to both sides. So 95% is in the middle. So this is going to be 2.5 on each end. So this will be 0.025, and this will be 0.975 here. So that critical value would be actually from the 0.975. 0.975, comma, 14. And I get 2.145 is what I'm getting. Which is exactly what they got. So our test statistic, or it's not test statistic, our margin of error is the 2.145 times that standard error. 12 is the sample standard deviation for sample 1, divided by 15 is its sample size. 9 is the sample standard deviation for sample 2, divided by 20 is its sample size. So that's multiplied by, again, by that critical value. We get 7.925 as our margin of error. So we take our point estimate, which was the 11.2. We subtract that to get the lower end of 3.3. Take the 11.2, add that to get the upper end of 19.1. Now that could have been, this is 3.275 and 19.125, but they rounded them back. So we're saying we're 95% confident that the mean drop in blood pressure is between 3.3 and 19.1. Now there's a relationship between this and our hypothesis testing. Since the interval here for the difference does not contain 0, that would say there is a difference. Because if the results were close enough that there was not enough evidence to say there was a difference, 0 would be in this interval. Since 0 is not in this interval, then we would reject that null hypothesis. The second way for doing degrees of freedom, if you're using the calculator, this is what the calculator does. This is what I was talking about before, a degree of freedom calculation. I'm not going to step through it because it is an ugly calculation, and for this course we won't use it. The only way we'll use it is if the calculator is doing it for us. So let's enter this in the calculator. We had the option of doing data or stats. We're going to do, well, let's go there. We're going to go to stat, test. This is going to be a interval, so we got arrow down here. Two sample t interval. And what we have here are the statistics. So we're going to switch over to stats now again. Our first mean is 28.3. Our first standard deviation is the 12 out of the table here. Oops, our first sample size was 15. So that's just this first column of the table here. Our next column, X bar 2, is 17.1. Is the average decrease in the second sample. The standard deviation of the second sample is 9. And that second sample size is 20. Confidence level is 0.95. Pooled or not pooled, we're going to say no, because remember, no means the calculator is going to have to go through that long calculation, but we don't have to do it, so we're going to let the calculator do it and be more precise. We'll hit enter. Well, that's figuring out. We're going to jump to the next slide here. And you will see that we get that same result. 3.5912 to 18.809. So all they're saying here is going through the different options as you select buttons on the calculator that we've already entered in. Okay, so if the two population standard deviations are known, then we can do z-tests and z-intervals for that difference. It was widely used in the past but we don't use it anymore. Now, because of computers being able to do the Z calculation was a lot easier to do, so we did it. The T calculation is going to give us pretty much the same result if the numbers are right, so we don't need to worry about it anymore. So basically, we're not going to use that anymore for this course. We're not going to use the two samples Z test or two samples Z intervals. You can see this is the pooling, the standard deviation that they talked about. We opted not to do that. As you pool the standard deviation, that means you don't have to do the degrees of freedom calculation. You can add the two sample sizes and subtract 2 to get your degrees of freedom. This only works if the standard deviations for both populations are known. So then this is just go through the formulas. The test statistic here is a little bit different. The standard error is a little bit different if you have the pooled standard deviation. Instead of having both standard deviations having to go in that formula for the standard error, it's this pooled standard deviation times that. That's still a weighting between the sizes of the two samples. And degree of freedoms, of course, is you add the two sample sizes together and subtract 2. Like I said, for this course, we're not going to use that Z test really for anything. If there are two samples, if there's two populations we are comparing, we're going to use a T test for the means. Now, when we get to the proportions, we will use a Z test because proportions, remember, always use a Z test. So a summary of what we learned in this section. We learned the difference between independent and paired samples. Our next section is going to be on those paired samples. We did the test for p-value and critical value for those independent samples. And we constructed the confidence intervals for the difference between two population means for independent samples. So that is it for this section. I'm going to end this recording. We'll do a new recording for the next section.